All right, when we left off on last Friday, we were talking about NMOS transistors, specifically operating in the triode region. So today, let's continue that discussion by looking at what happens when VDS is very small in comparison to the quantity VGS minus VTH. So what we would call deep triode region. So in the deep triode region, where, again, VDS is much less than VGS minus VTH. And I'm sure all these people are just saying that they're here. Yeah. One thing that I want to point out real quick, I might refer to something called the overdrive voltage occasionally. The overdrive voltage is simply that quantity VGS minus VTH, or how far passed on the device is. I'll try not to do it too much, but if I ever do say that as a shorthand, I'm simply meaning VGS minus VTH. So in the deep triode region, where VDS is significantly less than VGS minus VTH, we can see that ID, our drain current, is going to be approximately mu n C ox W over L VGS minus VTH multiplied by VDS. We're effectively saying that this VDS square term here is so small that it doesn't matter. Well, we have now a simple linear relationship between ID and VDS, right? So what we're really looking at is this region right here, where all of our drain currents for different values of VGS minus VTH, if I could draw, would look effectively linear. They'd look like simple straight lines. So in the very deep triode region, we can say that our Mosfet transistor is behaving as if it were a voltage-controlled resistor. So we're going to call that guy R on, and it has a value of VDS divided by ID would be 1 divided by mu n C ox W over L VGS minus VTH. So this is only valid in the deep triode region, but we now have a means by which to use a Mosfet transistor as a resistor. This is interesting, okay? When we first started talking about Mosfet transistors, when we had the source voltage and the drain voltage grounded, the transistor itself behaved like a capacitor. And we can make that capacitor larger by simply increasing the physical dimensions of the channel width and channel length, right? So it does. So if the oxide capacitance has some certain value, if we want to hit a specific capacitance, we simply choose a width to length ratio that gives us the capacitance that we're looking for. Now we see how we can use Mosfet transistors to develop resistors in an integrated circuit. So in a real IC, a lot of the circuit elements that we would consider traditional resistors, et cetera, and capacitors and things like that, are all actually implemented just by specifically biasing MOSFET transistors in different ways, which means we can make things really nice and compact and small. The reason, excuse me, why I say that specifically, for those of you who don't get so turned off on this subject matter by the time you get out of 336 and choose to take 438 as one of your senior options next year, the integrated circuits class, we'll go through what it would look like to develop N-well and P-well resistors, high-res poly resistors, and things like that. And we'll see that while we can make good, stable resistors using those tricks, they are typically extraordinarily large in comparison to a single transistor-based device. So there are trade-offs to be seen there. Okay. So we have talked about what's happened. Let's go back up to our picture here, okay? So we have VD greater than 0, but less than the quantity VGS minus VTH in this top picture. So what do you think is going to happen when VDS is exactly equal to VGS minus VTH, or our overdrive voltage? What's going to happen to this charge density profile? So I'm going to draw a picture. Lots and lots of pictures in this section. So here we have our substrate. Let's see. Need my gray for my oxide. Here's my polysilicon gate. And we're going to leave our source grounded. We're going to have VGS is greater than VTH so that our device is on. A channel should be established. But now we're going to say that VDS is exactly equal to VGS minus VTH. So what we should see occur with our charge density distribution as a function of position is something like this, okay? Where this is our X direction. And this condition right here is what's called pinch off. So this triangle is full of free electrons, okay? So when pinch off occurs, we are restricting the amount of free electrons that can move over into the drain. So we should expect to see that our current is no longer able to increase, all right? Because we have that pinch off condition, all right? So when that current can no longer increase, a change in VGS does not give us a change in our drain current of ID. This is what's called our saturation conditions for a MOSFET transistor. Change in VGS, or an increase in VGS specifically, does not cause a change in our output signal, which in this case is our drain current. So if we revisit our device current integral for this condition, where we're integrating from, if I can stop pressing this button on the side of my pen, x is equal to 0 to L ID dx is equal to, integrating from v is equal to 0 to v is equal to VGS minus VTH mu n C ox W VGS minus V of x minus VTH, excuse me, dV. This guy gives us a drain current. Hand would stop moving. ID is equal to 1/2 mu n C ox W over L VGS minus VTH squared. So this is for VDS greater than or equal to the quantity VGS minus VTH. So this equation, let's say explicitly here, defines how our device behaves in the saturation region. And it should be intuitively obvious why it's true if we understand what saturation means, meaning increase in VGS does not create a subsequent increase in ID. And it's the exact same equation we saw here for our parabolic arc that was limiting our maximum values for our currents. So the saturation current is the exact maximum current that the transistor can supply for a specific value of VGS minus VTH. So if we were to edit this picture, we would see that we simply have flat lines, so representing our saturation current. So everything to the right of that parabolic arc is saturation, everything to the left is triode, everything very close to the origin is deep triode. So we have pretty much fully developed our IV characteristics for our Mosfet transistors here. Now, if you recall, the characteristic curve for a BJT looked similar to this, except that saturation was on the left where it was increasing and forward active was where we had a constant value. So that can be a little bit confusing. The reason why the saturation region was the thing prior to that is because there, for a BJT, saturation is due to an increase in bias current, not causing an increase in collector current. Here, we're basing things off of voltage. So before we had effectively a current-controlled current source model. Now we're using a voltage-controlled current source model, and it causes this little disconnect. So I just want to be really, really clear with you guys that while these curves look extraordinarily similar to what you would see with a BJT, the definitions for the operation are significantly different. For the operational regions are significantly different. Okay, I don't think we are going to talk about that. All right, so let's talk about now, or I guess first, does anybody have any questions that I need to address before we move along to something new, but it's also kind of something old? All right, so let's look at this picture right here again then, where we are in saturation. What happens if VGS is greater than VGS minus VTH? What's going to happen to our charge distribution? Or a better way to put it is what's going to happen to the location where pinch off occurs. It's going to move further to the left. Absolutely right. The larger this voltage VDS is, the smaller X value the pinch off location has. So it's going to move that pinch off location to the left. And so what's happening there is we are lowering the effective length of the channel. So this is a phenomenon called channel length modulation. It is effectively the exact same thing as the early effect that we saw in BJTs, where when VCE was significantly large, the width of the base region got smaller, and so we saw the current increase. Here we're seeing the dimensions of the channel decrease, which also causes a subsequent increase in current. So let me write this out. Oh, good God, no, don't open up mail. So since this is another thing that is going to be a great theory question, I can write it down. Since the position along the channel where pinch off occurs is dependent on VDS, device current is not actually constant. In saturation region operation. Instead, the device current, excuse me, depends on a channel length modulation coefficient. Lambda as ID is equal to 1/2 mu e Cox W over L VGS minus VTH quantity squared times 1 plus lambda VDS. Now, obviously, this effect only occurs when we're in the saturation region because it is telling us what's happening while we shift our pinch off point to the left, and we don't have pinch off in triode. So it's only applicable within the saturation region, okay? That parameter lambda represents the relative variation in length for a given VDS. So here's another important distinction between a bipolar junction transistor and a Mosfet transistor, okay? In a BJT, we had no control whatsoever over the early voltage. If we were to design a device, the base width is going to be the base width. It has to be very small because of the regions that we discussed. For a Mosfet transistor, if we want to reduce the effects of channel length modulation, what could we do? Any thoughts? So it represents the relative variation in length, meaning that if we make the length larger, gamma is smaller. Now, if we look at our device equation, what does making the length larger do? Makes ID smaller, but we could just make the width larger as well. As long as we maintained a constant W over L ratio, we would get the exact same device current, but we could minimize our effects of channel length modulation. So this is something that's much more under a designer's control than the early effect is. So we are going to be neglecting it an awful lot under the assumption that we simply make our transistors big enough to where it doesn't really matter. It becomes extraordinarily prevalent though in short channel devices, obviously. All right, so with channel length modulation included, let's draw a quick picture of what's going on here. This is going to be ID as a function of VDS. We're going to see that it has this quadratic-like or parabolic curve until it hits this point, which is arbitrarily VGS minus VTH, and then without channel length modulation present, it would just be flat, but instead we see a linear increase in our device current as VDS increases. CLM. And just to be clear here, here is our saturation region. Here is our triode, and down here is our deep triode. Don't need to talk about sub-threshold operation. That's well beyond the scope of this class. All right, so Mosfet transistors can be used as amplifiers as well. So the next bit that we're going to be talking about is developing our models so that we can move along to the next chapter where we're going to explore the different amplifier topologies and all that kind of good stuff. The first thing that I would like to talk about is what's called the transconductance, which we had transconductance for a BJT and is representing the exact same thing. Change in the current due to a change in the voltage. So let's move along to here. Transconductance, all right. So transconductance is defined as a MOSFET's ability to create variations in drain current due to small changes in the overdrive voltage VGS minus VTH. So mathematically, Transconductance is defined as the change in drain current with respect to the change in VGS, since VTH is nominally a constant, while holding the quantity VDS to be a constant value. All right. So using this definition, we can find that our transconductance is mu n C ox W over L VGS minus VTH. With a little bit of mathematical manipulation, we could express it as 2 mu n C ox W over L times ID. And our third representation, twice ID over VGS minus VTH. All of these represent the exact same thing. It's just allowing us to determine the transconductance based on what different parameters we know about our device's operation point, okay, or the quiescent point. These are all valid specifically within the saturation region of operation, okay? Now, we are also going to have a transconductance in the triode region. Yes? That is correct. VGS minus VTH. So in the triode region, increases in VDS still increase our current flowing in our device. So we're going to have a specific transconductance relationship there as well. So we'll have GM is equal to mu n C ox W over L multiplied by VDS. And typically speaking, the transconductance is much larger in the saturation region than in the triode. So we want to have our, if we're going to use a Mosfet transistor in an amplifier circuit, we overwhelmingly want them to be biased in the saturation region more so than the triode region. So just like our BJT amplifiers, we had them biased in the forward active region. We want our Mosfet amplifiers biased in the saturation region where the device current is effectively steady. Now, with channel length modulation effects present, our transconductance is going to look a little bit gnarly. So this is still technically saturation, but we are not neglecting channel length modulation. We're going to have mu n C ox W over L VGS minus VTH times 1 plus lambda VDS, which is the same as the square root of 2 over mu n C ox W over L ID divided by 1 plus lambda VDS. And I'm going to write C, that does not look like a C, that looks like a G. CLM, letting you know that this is when channel length modulation effects are included. All right, so this is our basic transconductance for our helping us develop what's going on with our small signal model for the most part. There is a second transconductance that we are largely going to neglect in this class, but I'd like to at least introduce it to you. And that is what's called the body effect transconductance. So, since a potential difference between the source and body of a Mosfet has an effect on our threshold voltage VTH, the body effect then also influences the overdrive voltage VGS minus VTH, which in turn influences our drain current ID. So we are going to define our body effect transconductance as GMB, B for body effect, and it is the change in ID with respect to the change in the body source voltage. Bless you. So we have mu n Cox W over L VGS minus VTH times a factor of negative the derivative of the threshold voltage with respect to the body source voltage, since the change in threshold voltage with respect to the body source voltage is equal to this guy. So I'm effectively saying here that I can swap the subscripts by on my body source voltage to go to a source body voltage by introducing a negative sign. And then from our definition of the body effect, we get minus 1/2 gamma, our body effect coefficient, times twice Vf plus VSB to the negative 1/2 power. Substituting this relationship into our prior one, our body effect transconductance is simply our transconductance without body effects present multiplied by a term of gamma over 2 square root of twice Vf plus VSB. And we'll talk about where that is going to show up in our small signal model momentarily. All right. So let's see. Let's move along down here. Large signal models. Not something that I regularly use, to be entirely honest, but it's in the book, so we'll define it. Might find it a little useful every now and then, but for the most part, probably not going to use it too much.
Dr. Hardman?
Yes.
I'm sorry, can you scroll up for a second? I was just finishing that last equation.
Yep.
Okay, thank you.
Yep. All right. So our models here, let me just double check. I think, yeah. This is going to be the last topic. Our large signal model and our small signal model is going to be the last topic we're going to cover today. We'll work on PMOS transistors on today's Monday, Wednesday. So large signal models. So let's start with the one that we would likely use the most, our saturation model, okay? So we're gonna, dang it, go away. We're gonna have 3 different models depending on our conditions. And we're gonna be, for the most part, treating this guy as a 3-terminal device. So here is our gate. Here is our source. And over here is our drain, okay? So between the drain and the source, we are going to place a dependent current source, right? Because we see current flowing from the drain to the source. For, oh, why did I do that? For the saturation region, this current is 1/2 mu n Cox W over L VGS minus VTH squared times 1 plus lambda VDS, where we're saying channel length modulation effects are present. So here's where it's going to be, so far things are looking pretty similar to a BJT, right? We have between those right two, or the rightmost terminal and the bottom terminal, we have a dependent current source. And we saw in a BJT that that current was controlled by a voltage drop between our leftmost terminal and our bottom terminal. And that's going to happen here as well. But in a BJT, we saw that occurring over a diode, right? Here, it occurs over an open circuit. Now, it might not seem super obvious to you why that is, but it's because between the gate and the channel, there is that capacitance formed, right? And so this is our large signal or DC model. So it seems reasonable that we would treat that relationship as the DC equivalent of the capacitance that it's representing. We're going to see that the input impedance for Mosfet transistors is astronomically large usually for this very region as well. There's a capacitor in there messing things up for us, or really helping us out if we're looking for large input impedance. So this is our model valid for VGS greater than VTH and VDS greater than VGS minus VTH, or the saturation region. I'll put that here. Our second small signal model we'll concern ourselves with is the one for our triode region. And it's going to look effectively identical, except that the value of our current is going to be different. Gate source drain. Here, our current is, and let me go, the textbook uses this weird thing where it's got extra factors of 2 to give a factor of 1/2 in the beginning that I don't much care for, so I'm not going to use it. Mathematically, it's identical, it's just confusing to me. Mu n Cox W over L VGS minus VTH times VDS minus 1/2 VDS squared. This is valid for VGS greater than VTH when VDS is less than VGS minus VTH. Which we have defined to be our triode region. And then lastly, we can develop one for our deep triode region. I guess technically we could develop one for the cutoff region as well, but it would just be, there's an open circuit between all the terminals because no current's flowing, and that seems kind of dumb to draw. So in the deep triode region, instead of having our current source, we model the linear relationship between voltage and current as a resistor. So those are our large signal models. And let me explicitly say over here, this is for VGS greater than VTH and VDS is much smaller than VGS minus VTH, which we have described previously as deep. So there's our large signal models, and from this we could go through the efforts of explicitly deriving our small signal models like we did with bipolar transistors, but I am going to kind of skip through a little of that. So small signal models, let's come down here. Oh, did everybody have time to copy this down before I jumped ahead? All right. Small signal models, this is where you guys are going to get so much practice. These are the ones that are used to analyze variations around a DC operating point. We are going to consider them to be useful for saturation region only, effectively, because we want our amplifiers to be biased in the saturation region. Yes. No. This guy right here, all these large signal, is the DC model. What we're about to do is the AC models for amplifiers. Yeah. So we are about to develop our AC models here. All right, so let's start. With this guy. So between the drain and the source for the small signal model, or between the emitter and the base for a small signal model of a BJT, let's start there. What did we have? So yeah, between the base and the emitter. No, base and the collector was R pi, wasn't it? Collector was on the left-hand side. I'm going to draw the damn thing. Oh, excuse me. No, okay. No, you're right. So between the emitter and the collector, you're 100% right. Between the emitter and collector. So for our BJT, sorry, I'm just going to draw this because now I'm confusing myself like a jackass. So we had R pi, here was V pi, we had GM V pi, here was our collector, down here was our emitter, right? Okay, that's what we had. So between our gate and our source, we're still going to see that very, very large input impedance. We're going to treat that as an open circuit. Even in our small signal analysis, we are going to treat it as an open circuit. So plus, minus, lowercase VGS is how it's usually written. On our right-hand side there, between the drain and the source, we are going to have effectively the exact same thing we had in our BJT small signal model. Simply the transconductance multiplied by our input voltage, all right? Where the input voltage is VGS. So this is our baseline small signal model. When we include other effects, we are going to be adding things to this model, okay? So this is our baseline. Now, what happened when we included the early effect in a BJT? We added a resistor between our collector and our emitter. Well, our channel width modulation is effectively describing the exact same thing as the early effect, so it's going to wind up putting a resistor between our drain and our source. So let's sneak that guy in here. So here's our gate, source, GM, VGS. We are going to call this guy, let's see, what do they use? R naught. Here is our drain, where R naught is the change in VDS due to a change in our drain current. So that's just going to be 1 divided by 1/2 mu n C ox W over L VGS minus VTH squared times lambda, or in a much more simple expression, 1 over lambda ID. So this is with channel length modulation. Lastly, we're going to include channel length modulation and body effects. And so we saw that we had a body effect transconductance. So we're going to have GMB multiplied by the effectively input voltage for this guy, which is VSB, some source body voltage. And so between our source and body terminals, we now have some voltage, VSB, that we need to account for. So this is what our small signal model would look like, with body effects included and channel length modulation included, where we've already defined what our parameter GMB is. Probably not going to see that in this class. Just if you go through into 336 and then 438, it's going to come into play. So I'm just hedging my bets that at least one of you is going to need to know what the hell this is when you become a senior. All right, so that's the last thing that I wanted to talk about with regards to material today. So let's circle back around to the homework. And because you're only given one shot on problem 3, I figured we might do that guide together. But let's go look through everything and make sure stuff's legit first. All right. So problem 2, we are told, let's see, an N-type MOS transistor can be used as a resistor when provided with a small drain source voltage. That's true, we've seen why that occurs. If the supply voltage, meaning specifically VG, or I guess a better way to put it would be VGS, is 1.2 volts. Find the minimum on resistance that can be achieved for a transistor with a width to length ratio of 10 and a threshold voltage of 0.1. So I believe this is just the direct application of our parameters. One thing that we are not told is what mu n times C ox is. If we jump back out to homework set 8 and scroll down, Mosfet parameter mu n times C ox is expected to be 200 microamps per volt squared. So use that unless you're told something different. So you were technically provided enough information, they just didn't do it where you would expect it. All right, so let's circle back around to that. So we have mu n times C ox, we have our W over L ratio. We are given VGS, although it's not explicitly stated as VGS, and we're given VTH, so that's just plug and chug, easy peasy. Problem, let's jump over to 4 real quick. Problem 4 says an engineer wants to create two current sources with identical MOSFETs. The drain source voltage of M1 is 1.25 volts, and the drain source voltage of M2 is 2.25 volts. If the current of the MOSFETs are to match to within 1%, meaning 0.99 ID2 is less than ID1 is less than 1.01 ID2, then what is the largest tolerable value for lambda? That's just mathematical manipulation, right? You know that ID is going to be the exact same thing multiplied by a factor of 1 plus lambda VDS1 is 99% or whatever of ID times 1 plus lambda times VDS2. Manipulate, figure out what lambda has to be to make both of those constraints true. Easy enough. All right, so now let's go back to problem 3. 9 problems. And effectively all you're asked to do is to determine whether the device is operating in the cutoff region, the triode region, or the saturation region. We are using an assumed value of VTH is equal to 0.4 volts. It was what was given on that list of parameters I showed you. So let's look at this first guy, okay? Now this is the MOSFET model as it shows up in LT Spice, specifically the model where the body is tied to the source, which is what's going on right here. So the arrow is on the body instead of the source in this particular model for whatever, but the source is the guy that's tied to that. So for our top leftmost transistor, what's VGS? I disagree. It's 0. 1/2 of a volt minus 1/2 of a volt is 0, right? So if VGS is 0, is it less than our threshold voltage of 0.4 volts? Yes. So what mode is this guy working in? It's off. Okay, easy enough. For this top middle guy, what is VGS? 1. Okay. So VGS is 1. 1 is greater than 0.4 volts, so it's on. So now we need to figure out whether it's in the triode region or the saturation region, right? So VGS minus VTH is going to be 0.6 volts, right? 1 minus 0.4. VDS is 1.5. So is VDS greater than or less than VGS minus VTH? Greater than. So what does that mean? Saturation. Yeah, if VDS is greater than VGS minus VTH, we are in saturation. Let's look at the top right guy here. So we have VDS of 1 volt, which means we have a VGS minus VTH or overdrive voltage of 0.4 volts. So we're definitely on. VDS is 0.5, right? Or excuse me, no. VDS is 0.5 minus 0.5 is 0. So VDS is less than VGS minus VTH, which means that guy is operating in the triode region. Let's look at this next row. I'm going to pick on Pozniak again because I like him. How is this top left or middle left guy? What's its state? So let's do it the formulaic way that we've been doing it, right? What's VGS here? 1. Okay. So what's VGS minus VTH? Okay. What's VDS? So D is up here, it's grounded. S is right here at positive 0.5. So VDS is negative 0.5 volts. So is VGS minus VTH larger or smaller than VDS? VGS was 0.4. VDS is negative 0.5. VDS, yeah, VDS is less than VGS minus VTH. And so this guy is operating in the triode region. All right. I'm going to yell at somebody on Zoom. I'm going to make you guys participate. Let's see. I got 10 participants. Who am I going to pick on? Close that window. Let's see here. Kevin, are you paying attention?
Yes, sir.
All right. I want you to tell me what's going on with the middlemost transistor here.
So BGS minus BTH, no, BGS is 1.5.
Okay.
BGS minus BTH is 1.1.
Okay.
BDS it's 0.5.
Okay.
So that means BDS minus BTH 1.1. So BDS minus BTH it's over BDS, and that means it.
Sorry, keep going.
That will be the triad.
Absolutely correct. All right, Ronnie. Middle row, rightmost one. This one's kind of wonky looking. So the drain and the gate are connected together, right? So VD is exactly equal to VG. Okay, so you're saying, yeah, so VGS would be 0.5 minus 0.50. Absolutely correct. Okay, so that means it's off, easy enough. All right. Mr. Washington, do the one on the left, bottom left. So let's start with what VGS is. Let's start there. Let's not worry about subtracting anything from it until we know what it is to begin with. So what's the voltage applied at the gate? What's the voltage applied at the source? All right, so what's VGS? It's the gate minus the source voltage, right? So positive 0.5 volts. Is that greater than the threshold voltage of 0.4? Sure, so it's on. And we have VGS minus VTH is equal to 0.1 volts. What is our drain voltage? 0. And again, our source voltage is minus 0.5. So what is VDS? Positive 0.5. So VDS 0.5 is greater than VGS minus VTH of 0.1, which means this guy is operating in what region? Saturation. When VDS is greater, it's saturation. When VDS is less, it's triode. Mr. Anderson, tell me what's going on with transistor M8. Okay. It's positive 1 because 0 minus negative 1 is positive 1. Okay. So VGS is 1 and VDS is also 1. So this guy is going to have to be in saturation because we have to subtract the threshold voltage from VGS. So VGS minus VTH in this case would be 0.4 volts. VDS is 1 volt. 1 is greater than 0.4, right? Yeah, so everything you did was correct except forgetting to subtract the threshold voltage from VGS. All right, let's see. Who on Zoom can I pick on for this last one? Vitaly, are you paying attention?
Yeah, sure.
Great. Do the bottom right one.
So VGS is 0.5.
Okay.
VGS is it 1?
That's correct.
So VGS minus VTH would 0.1.
Okay.
And at this point, we have VGS is bigger than VGS minus VTH, so it's in saturation.
That is correct.
Okay.
So that's you only have one shot at this. All the 9 different permutations done in about 5 to 6 minutes, right? This is about as easy as it's going to get. Unfortunately, everything past this point is going to be a little bit more difficult. All right, so that's enough out of me for today. We're going to knock off about 10 minutes early. You should be able to do all of your homework problems to this point, but I believe Dr. Patari extended the due date until Thursday. So I guess he feels like he's going to be going slower or something. I don't know. We're going to cover PMOS transistors on Wednesday, and depending on how long that takes, a lot of it is just paying attention to the signs of things and adopting a specific convention. Then we might move into chapter 7, which is Mosfet amplifiers, where we'll talk about biasing. So we'll start talking about biasing at the absolute latest on Friday. All right, see you guys on Wednesday. Have a great rest of your day.